Thank you. It's always inspiring to be back in Oxford. It always reminds me of Jude the Obscure. The question that I'd like to consider with you tonight is this one: does the world embody beautiful ideas? It's a strange kind of question because it seems to relate two different conceptual worlds: the world of embodiment, which is the physical world, and the world of beauty and ideas, which is not the physical world. It's a conceptual world. So what does it mean to embody beautiful ideas? Well, embodying beautiful ideas, if you think about it, is what artists do. They have concepts, visions, creative inspirations, and then they try to make embodiments of them, either as physical objects or musical compositions, but taking them into the realm of physical reality and sensation. So another way of formulating our question is it useful to think about the world as a work of art? And if it is a work of art, is it a good one? That's the question that's the kind of question we'll be considering. There are historical episodes that are relevant in considering this question. At the dawn of the Renaissance, artists wanted to portray the world accurately. They wanted to portray the world as it's actually sensed, but on a two-dimensional canvas. So this made a problem that was solved by this art-inspired science of perspective. This was a great crossroads of art and science, and although the scientific revolution is usually dated a little later, to me this was the real beginning of the scientific revolution. And it has great light to shed on important concepts that we use today and on our question. So, let's look at it. Viewed from above and afar, train tracks run in parallels, if you're going on a long straight path, and they never meet. But that's not necessarily the way it looks from other perspectives, like this. So there's a natural question that arises that's at the heart of the art of perspective, which is, what sorts of images represent the same object seen from different places, from different perspectives? This question leads to the subject known as perspective in art and as projective geometry in mathematics, where precise answers are supplied. The central soul of the subject is that you can change the image you can have many different images that represent the same object. And conversely, if you consider an object and consider all the different perspectives from which it might be represented, there are many changes you can do to the object without changing the totality of perspectives. For instance, if you rotate the object, the way it looks from any particular place will be different, but the totality of representations from all possible perspectives will be the same. So again, we have the possibility of change without change. Change without change, I'll show you, is the essence, or I'll show you, is a very fruitful concept, the essence of the concept of symmetry as it's used in mathematics and physics, that leads to the modern understanding of fundamental interactions. People find symmetry beautiful, both intellectually and artistically. We can prove this empirically. Here is something that I think anyone has to like when they do it. Remember when we looked at those train tracks, we saw that they appeared to meet in a point on the horizon, the so-called vanishing point or point at infinity. And if we had lots of parallel train tracks, they would all meet at one point at infinity. If we had a different set of parallel tracks pointing off in a different direction, they'd meet at a different point at infinity. Now consider the problem which occurs in art of trying to represent accurately what a tiled floor made of squares looks like from different perspectives if you want to draw it. There will be a horizon where all the parallels meet at infinity, and you start with the appearance of one particular square, and then the problem is to find the appearance of all the other squares on the tiled floor. And here's how you do it. So you have this original square, and you have the horizon, so these points have to meet at the point at infinity for that family of parallels, as these lines meet at a different point at infinity on the horizon. And then the key insight that makes this construction go, that allows you to go further, is to realize that this red line, the diagonal, must be parallel to other diagonals on the tiled floor of the other squares, so we can draw the diagonal of neighboring squares by connecting these points to the point of infinity, at infinity, that's defined by the red line. So then we have the diagonals of the neighboring squares, and we have the place where the diagonals meet the side of the square, so we have one of the corners, the vertex of the square, and then we can draw through these 2 points a side of the square that goes off and meets at infinity these parallel lines, and we can draw a side of the other neighboring square that does the same thing. And then you can keep going. It's a magical thing to do. I've done it dozens of times, and each time I do it, I get a thrill. And then if you just erase all the diagonals that you used in the construction and color them all the same way, blue, you get this figure, and you've created the solution to the problem of getting an accurate representation of a square tiled floor from an unusual perspective. This inspired enormous enthusiasm and creativity in the Renaissance. A few years later, artists such as Perugino were creating masterpieces like this, and you can just see the joy of Perugino himself reflected in the joy of these figures that are so happy that they can be dancing on an accurate square. Okay, so now we need so we have a powerful idea of change without change, symmetry, that people find beautiful in artistic creation. I'd like to show you now a more ambitious form of perspective and symmetry that is being explored in modern art that turns out to be at the core of our modern understanding of the fundamental forces. This is called anamorphic art or anamorphic symmetry. It's when perspective goes local. So here it's easier to show than to tell exactly what it is. And here you see the idea. The idea is that if you allow yourself to include not only changing the place from which you look at something, but also allow there to be media, curved mirrors or lenses that reflect your object, you find a much wider range of representations that still represent the same underlying object. So it's not just perspectives, but also in the conventional sense, but also distortions that are get allowed. A much wider class of images all represent the same thing, and you have a much larger kind of symmetry. There's a much larger class of things you might have done to your object without changing the whole range of representations. This is also the central idea of Einstein's general theory of relativity. In that case, what you want to do is allow different representations of space and time that use different so-called coordinate systems that can be curved meshes, more complicated representations than just the rigid Euclidean grid that is assumed in Newtonian physics. Now, to enable such curved spaces and distorted representations to represent the same space and time we live in, the same space and time that we can also represent with less distortion, we have to allow the possibility of an analog of curved mirrors or lenses. In that case, the medium is called the metric fluid. It encodes the distortions, the curvature of space and time, and allows us to reconstruct the same image from many, many different representations. Now, John Wheeler had a real gift for representing physical concepts in poetry, and he did that in the case of the black hole, where he invented the name for the black hole. In the case of concepts like mass without mass, charge without charge, things that among physicists are kind of buzzwords that we love to use. And he had a yoga, a two-line description of the general theory of relativity, which I'm going to correct and build on. His yoga, his original yoga without the stars, was that space-time tells matter how to move, and matter tells space-time how to curve. This is the essence of Einstein's description of how gravity works. Space-time is bent by the presence of matter, and matter does its best to move according to straight lines in this curved landscape. But how exactly does space-time curve? And that's where this concept of symmetry comes in. You want to have the anamorphic possibility that many different representations of the equations lead to the same consequences. And that gives you very special equations. I'll elaborate on this thought, but at the moment I want to keep it artistic. So our theory construction involves choosing the objects that transform, the substances, the sorts of transformations we want to allow, and the enabling media that make those transformations legitimate representations of the same underlying laws of physics. This art of theory construction deeply resembles the art of artistic creation. Here I'll show, this is a representation by the artist of how he dreamed up that anamorphic art. You decide what substance you want to represent. You want what the substances are. You choose how you want to be able to transform it and still have the same underlying object. And then you supply the materials, the media, that allow this to be transformed into that. So you specify the substances, specify how you want to allow them to look, and then you specify the enabling materials that allow them to, under their influence, look the way you wanted them to look. And if we demand that there are many, many, many different ways to represent the same physical situation, we get led to very specific materials and very specific equations, as you'll see. For wider use, when we go beyond general relativity to describe all the other fundamental forces, we'll want to change the yoga a little bit, refine it, because there are other things that matter does besides bend space and time. And a more flexible formulation that you'll see generalizes is that the metric fluid tells energy momentum how to flow, so it directs one aspect of matter, and energy momentum tells the metric fluid how to flow, how the metric fluid should respond, not to all features of matter, but to its amount of energy and momentum. Now, let me be a little more precise about this notion of symmetry as it applies to physical law. I hope it's clear how symmetry applies to physical objects. The idea of symmetry applied to physical law is a little more subtle and takes, now it can use some spelling out. And a wonderful example goes back to Galileo. Galileo described an experiment that you do on a ship. It's a thought experiment, but people at the time had done this kind of thing. They were familiar with riding on ships. If you have your ship still at port and you're in a closed cabin and you've thoughtfully brought along some animals and fish and balls and a friend to throw things, you can do various experiments that show you that throwing it one way is as easy or as hard as throwing it the other way, that if you drip down water, it falls straight down, the fish swim in different directions equally well, and so forth. Galileo's thought experiment was just to say that if your ship is moving along in calm waters at a constant velocity, all these statements are still true. Have the ship proceed with any speed you like, as long as the motion is uniform and not fluctuating this way and that, you'll discover not the least change in all those effects. In other words, you can make a big change in the physical situation without changing the behavior of the laws of physics, or the behavior of the physical world. That's symmetry as it applies to physical law. Change that might have changed the way things behaved actually doesn't. This observation of Galileo later in the 20th century, when combined with the observation that the speed of light is constant and doesn't change in different, even when you're moving or not, leads to the special theory of relativity. So there's one aspect of the special theory of relativity that's especially pertinent and I think is especially beautiful and visual that I'd like to share with you. It's kind of counterintuitive, and it was the genius of Einstein to realize that it was possible to reconcile the idea that the speed of a light beam doesn't change with the idea that you can move at constant velocity. Because if you move at constant velocity, you might think you're catching up on the light beam, or if you're moving another way, moving away from it. And that should change the perceived velocity of the light beam. But according to the special theory of relativity, it doesn't. If you have a light beam and you're moving towards it, it still takes as long to arrive. If it's moving away, you don't catch up with it. If you're moving away, it still takes the same amount of time to catch up. But something does change. If you have a beam of pure light that's one color, and you're moving very rapidly towards it, the color shifts towards the blue end of the spectrum, and if you're moving away from it, the color changes towards the red end of the spectrum. Now, back in the 17th century, a great discovery of Newton, when he clarified the nature of color, was to show that once you disperse white light into its component colors, say using a prism, that those sub-beams of the light don't change if you do all kinds of things to them. If you reflect the red piece of the spectrum off a mirror, or pass it through lenses, or pass it through substances, no matter what kind of indignity you subject it to, it stays a red beam. And similarly for the other colors. And so in Newton's description of light, light was many, many different substances, one for each color, that couldn't change one into the other. Symmetry, this special theory of relativity, according to which when you move, the color of light changes, means that all these substances are really the same substance, just seen from other perspectives. And, I should say what this picture is. This is a picture according to the equations of electromagnetism, which obey the theory of special relativity, of a light beam where, unfortunately the colors are kind of washed out, I'm afraid, in this presentation, but you can see that they're bluish over here and reddish over here. If this was the source, and it's moving at about 7/10 the speed of light. If it's moving towards you, you would see this color. If it's moving away from you, you'd see this color. So that's the symmetry of physical law, showing that the idea and the power of the idea. The idea is that there are changes you can make in the state of the world that don't change the behavior of things. It's change without change. And the power of it is, it shows you that things you might have thought were different are actually different aspects of one underlying reality, just seen in different ways. When we come to explore less familiar realms than light and moving on ships, we have to rely not on pictures and thought experiments, but increasingly on equations. But that same symmetry, that same concept of symmetry, applies not only to the physical laws, but to the equations that describe them. Let me show you, and here we can make a really simple example that captures the very essence of the idea. The only equation I'll have in this lecture, x equals y, actually there's one more equation, you see, x equals y, that's what you'd be tempted to call a very symmetric equation. It's really simple, x and y are playing the same role. And in fact, it is symmetric according to the definition that we talked about. There's a change that doesn't change it, namely if you change x into y and y into x, the look of the equation changes, just as if you look at an object from different perspective, it looks different. Or just as if you look at a beam of light at moving different velocities, it looks like a different color. But the content doesn't change. x equals y has exactly the same content as y equals x. Whereas, if you started with a lopsided equation, and this is the other equation in the lecture, if you start with a lopsided equation like x equals y plus 2, that shouldn't be symmetric. It's not particularly nice. It's arbitrary. What is the 2 doing there? And sure enough, if you change x into y, this equation changes into y equals x plus 2, which doesn't mean the same thing at all. So it's not symmetric. Now, when we come to write down the laws of physics, we need to consider much more complex, much more elaborate kinds of transformations, but the basic idea is the same. We look for equations which can be changed so that they look very different, but after that change, nevertheless, they have the same content. So, in the case of objects, it was looking at it from different perspectives, or really going wild and allowing ourselves to invent media that allow us to make all kinds of transformation. In the case of relativity, it was moving past things. The laws of physics don't change, but although everything looks different. And in the case of equations, you change the objects in the equations, but the content doesn't change. In every case, assuming symmetry limits the possibilities and tells you about what kind of images you can have, or that the different substances, the different colors of light are actually the same thing, or that you're not allowed to put an arbitrary 2 to mess up the equation. So assuming symmetry is a very powerful guide to getting good description, special equations, and perhaps by extension of experience in relativity, perhaps getting the equations that describe the world. Now, to move from gravity, which is about space, or actually space and time, but basically space, to describing the other interactions, I have to introduce another concept. But fortunately, it's a concept for which there's an excellent metaphor, which is interesting in its own right. I'll use color as an entryway into thinking about extra dimensions. So this will prepare us for understanding the other interactions. This is a picture of a great hero of physics, mostly associated with Cambridge, not Oxford. Sorry about that. This is James Clerk Maxwell. You can see sort of a smile on his face and a twinkle in his eye and a toy in his hand. He's my favorite physicist. He's like got that spirit of the inner child. And what is this toy that he has? Why is he posing for a formal portrait with this silly toy in his hand? Well, this toy is actually a very powerful scientific instrument that Maxwell used to clarify the nature of our perception of color. It's actually a top that you can spin, and it has 2 rings, 2 circular rings around the center of the top, so these spin around to make little bands. And when you spin it fast, because of the persistence of vision, the color that you see is a mixture of the colors that are on the ring. And what Maxwell did in a very elaborate set of experiments extending over many years, many performed with his wife, was to demonstrate in great quantitative detail that you could match any perceived color on the outside, so any kind of paper that people could send him on the outside, by mixing just 3 colors on the inside in different proportions. So, although physically the things are very different, the colors, the bands that are making, the light, if you like, that's making these colors is very different, they appear exactly the same to your eye. This is the basis of all color photography and modern computer displays. You can get by with three primary sources of color. Mixing them in different proportions gives you any perceptible color, including, for instance, white here in this iconic figure. So when you see in your computer the option that says millions of colors, what that means is that you can mix three colors in different proportions with different intensities to get many different things that you perceive as different, but really there are just three underlying sources. We can describe this geometrically as a color cube. All the perceptible colors are in this color cube. You have different proportions of blue, from nothing to bright blue, green in different proportions, and red in different proportions. And I'm sorry, it looks much better on the computer screen, and of course in the book than it looks here. But it's I hope you can imagine what I've described, that this is a cube, and inside are represented the different perceived colors you get by mixing different amounts of blue, green, and red, and you get a three-dimensional figure, every piece of which represents a different color, and every perceptible color is represented. Keep that in mind. And now let's think of something that seems at first sight much more mystical, and in fact has inspired mystics over many centuries. The concept that there are extra dimensions. You can make jazzy pictures like this, where you imagine that there are little dimensions on top of ours. For example. Wouldn't it be neat if we could experience those? What would it be like? Well, we can, and in fact, we do. Remember the color cube? And now think about what you're seeing when you look at a computer screen. At every point on the computer screen, you're picking out a point in the color cube where you see the color. And so you're actually seeing, right before your eyes, this extra-dimensional space. If you want to look at it a little more mathematically, make it more convincing, perhaps, or more transparent. If you're a computer and you have to be told what to do, what to output, you need instructions about the time you're supposed to output at position X and Y, and then at position X and Y, how much red, green, and blue you're supposed to output. That's what you need to know. In this description, the RGB numbers look very much the same as the T and the X and the Y numbers. So they are playing an equal role. They are extra dimensions on top of the dimensions of space or even space-time. So the answer to the question, what do extra dimensions look like, is that you're looking at them. And now, with that insight, we can go back to general relativity and the idea that it's fruitful to look at distortions, crazy distortions of space and time, and demand symmetry, demand a medium that allows such distortions. We can also consider distortions of these extra dimensions that describe properties. These properties, uncannily, are called color. I don't know if it was genius or just luck that people in the early days, when they wanted to talk about these extra properties of particles, called them colors, but it turns out that color is an excellent metaphor in general for the driving properties of matter that are relevant to the other forces of nature. So, property spaces, like this property space of perceptible color, are the essence of our core theories of the electromagnetic weak and strong forces. The most familiar property space, because it's associated with the most familiar force, is the property space of electric charge. So, if you were a photon and you needed to know what to do, how to look at the world, what you need to know, according to Maxwell's equations, is the density of charge at every place in space and time. Okay. So photons see a one-dimensional property space. And the equations of electromagnetism have that one driving property of matter, property of substance, that controls the theory. It turns out that successful theories of the other forces of nature, the forces that were discovered in the 20th century that govern the subatomic and in fact subnuclear realm, obey very similar principles when you put them in this language of property spaces and symmetry. The only difference is that instead of in electromagnetism where you have a one-dimensional property space, to describe the weak force you need a two-dimensional property space, so two charge-like things, which however we can also represent as colors, and in the strong interaction you need three. So to put it in an image, photons, or the electromagnetic force, sees a one-dimensional picture of the world, one color property space. The weak interactions can be represented using two properties, so it's as if they see the world without blue. They just see two colors, red and green. And the strong interactions see three colors, just like we do, and you get the full image of my beautiful daughter. So we have this picture of the different forces where we have property spaces, like the color spaces, like the color cubes, either of one or of two or of three dimensions. And we can ask ourselves, if we want to guess symmetries, if we want to look for special equations that can describe this situation, we look for ways of we want to have very, very large classes of transformations that represent the same thing. In the case of objects, and by analogy, general relativity, it was the shape of space or of space-time that we wanted to be able to transform. Here we want to make transformations in property spaces, in these color spaces. This introduces a new kind of art, which is much less explored, and perhaps because it leads to such bizarre images. But instead of changing the shape of things as in anamorphic art, we can change the shape of their property spaces, change the shape of the color spaces, rotate those around or mix them. So here is what it looks like if you do that sort of thing. This is an image of a candy stall in Barcelona. And if we change red into blue and green into red and red into green, I believe we've done here. No, red into blue. No, red into blue, green into red, and blue into green. If we make those transformations, that changes this into this, which represents the same information as the original picture, but obviously looks different, just as you can look at the same object from different perspectives. And we can also then, the generalization of anamorphic art is to make changes in color which depend on the position. So to make distortions of a more general kind. So then, if we look for equations that have the same content, even though we make these drastic changes on the property spaces, we're led to very, very special equations. We need to introduce extra media, just as in the case of anamorphic art, we needed lenses or distorting mirrors. And in the case of general relativity, we needed a metric fluid to bend space and time. Here we have to introduce new fluids that shift colors around. Amazingly, and this was really the foundation of everything that came later, discovery by Hermann Weyl, that if you apply this strategy to a one-dimensional property space of allowing space-time dependent changes, rotations in the property space there, well, I won't describe the details, we get the electromagnetic fluid as the enabling material and Maxwell's equations as the properties it has to have. So we can state the yoga of QED in very similar ways to we stated the yoga of general relativity, since the underlying ideas are so much similar. The photon fluid, or also called the electromagnetic field, tells electric charge how to flow. That is, it should move as straight as possible in the property dimension. And electric charge tells the photon fluid how to flow, namely it should flow to allow the equations to represent the same content even though you've mixed up and distorted the appearance of it. If we apply that reasoning to two- or three-dimensional property spaces, we're led to more complex equations that follows the same logic. These are called the Yang-Mills equations. I like to say they're like Maxwell's equations on steroids. Because to enable this wider class of transformations, the enabling media have to be more intricate, more complex, but the mathematics allows you to control it. And concretely, for instance, in the case of a three-dimensional property space, if you want to allow arbitrary distortions of the three-dimensional property space, you need, instead of one photon, you need 8 different so-called colored gluons that can sort of undo or enable the distortions. But once you introduce that fluid, what now has like 8 photon-like pieces, the underlying yoga is exactly the same. The gluon fluid tells strong color charge how to move, and the color charge tells the gluon fluid how to flow. What the gluon fluid tells the color charges is move as straight as you can, keep your color as constant as you can, even though the background appears to be changing. And what the color charges tell you to do is obey symmetric equations. In this way, I'll leave the yoga of the weak interaction to you. It's exactly the same. In this way, we discover a common dualistic conception from which all the known fundamental interactions flow. That same yoga. And now we can circle back to our question about, does the world embody beautiful ideas? Because we can compare what we find in the world to what people thought was beautiful before they knew. And we find that such dualistic understanding is something people found beautiful long before anyone knew that it governs the fundamental laws of physics. In fact, it's the essence of Chinese culture, according to the yin-yang or Tai-Chi symbol, where the yin is substance and the yang is force, and each responds to and is shaped by the other. And in fact, each contains an aspect of the other, because in the quantum mechanics, when you have waves and particles, each takes some properties of the other. Building on that and comparing the world as we find it in these fundamental laws to the world that artists idealized, we find that our question has a beautiful answer. Empirically, we can go and look. What did people who were trying to embody their ideas of divine beauty come up with? And here's an example, and you see the kind of distortions that represent an underlying unity and an exuberance of color, very reminiscent of the kinds of transformations we found in the anachromic art. So anachromic art and anamorphic art are somehow things that people found inspiring and beautiful, even before they knew that they were at the heart of our accurate description, our deepest description of nature. Another aspect of the description of the world we find in fundamental physics and the sciences that grow out of it is that from simple rules you get a tremendous wealth of results from these profoundly symmetric equations that act according to ideal principles. You find the behavior of building blocks that can be made to, can be shown to give you all kinds of consequences, like computers, biology, chemistry, and artists, maybe. So, exuberance is, together with symmetry, I would say the deepest thing we find from the laws of physics, that simple rules can give rise to a wealth of form, exuberance of color, as I've shown, and also beauty of concepts, symmetry, this kind of duality. All of those things were things that people found beautiful in art, and they turn out to be the things that run the world. So that's a description of where we are now. Inspired by so much success, we get greedy. When we try to guess new laws, we can try to see if the same strategies will give us, that have been successful in the past, with creative variations, will give us more. Suppose we should unify all the forces and all the substances. Those would still, so unify our description of all those things, we'd still have two things. force and substance. And two is more than one. Is it possible that even these things are inevitable consequences of each other? That there are changes that you can make in the equations without changing the underlying laws that change the forces into substances and the substances into forces? Can we do this? Well, to accomplish that trick, it is possible. Otherwise, I wouldn't be leading you down this garden path. We must extend Galileo's idea that motion is something that doesn't change the laws of physics, to allow motion into new kinds of dimensions. These are called quantum dimensions. I won't attempt to describe the intricacies of quantum dimensions to you, but they're really interesting. Trust me, I've been there. It's not for the faint of heart, because all your substance changes into force and all your force changes into substance. You get really weirded out. But it's a rewarding experience. It's an eye-opener. Because it turns out to solve a problem that we very much want to solve. I mentioned the possibility of unifying all the forces. We have a three-dimensional color space and a two-dimensional color space for the strong and the weak interactions, and a one-dimensional color space, property spaces. You might notice that, and I've emphasized, in fact, that the description of all those things is very similar, and it's begging you to think that actually there's a bigger property space of which all those are parts, and there could be transformations among all the colors, not just separately among the strong properties or separately among the weak properties, but all of them. When you carry out that idea, you find that it almost works. As we observe the strength of the strong, weak, and electromagnetic interactions in the laboratory, they appear to be quite different. The strong interaction really does seem to be stronger. But if you make corrections for the fact that what we perceive naively as empty space gets corrected by the dynamics of particle fluctuation, so-called virtual particles or vacuum polarization or zero-point motion, all these things are the same thing, or asymptotic freedom, the thing I got the Nobel Prize for, all the same thing. If you correct for that distortion, the fact that the forces that are fundamental as they arise for the underlying particle at short distances get changed to our perception by effects of quantum mechanical fluctuations. If you make corrections for those and see if the underlying forces might all be equal, you find it almost works. Almost, but not quite. Now, if you want to have supersymmetry, if you want to have the equations that support this extra transformation, you need to introduce more stuff. Just as in general relativity you needed to introduce the metric fluid, just as in the strong interactions you needed gluons, in electromagnetism you needed the electromagnetic field. Here you need to add more stuff. And the more stuff also fluctuates, so it makes more corrections. And look what happens. When you allow for that more stuff doing its thing at very short distances or equivalently high energies, they do come together. So you could get a unification of the forces. And gravity, even gravity, fits too. Is this a revelation or an illusion? Because we don't have experiments at those extreme energies or short distances. Well, people are working very hard. You can see how they're getting tired here. At the Large Hadron Collider, this is 27 kilometers around in a gigantic circle filled with these magnets that are superconducting magnets operating at 2 degrees Kelvin. So this is the coldest region in the entire universe. In between galaxies, there's a 3-degree heat bath of microwave background radiation. This is even colder. A lot can go wrong with all this plumbing, so that's why they're tired. But thanks to the effort of these experimenters, we're going to have access to the large enough energies that we can see if the supersymmetric particles that we need to complete this latest step in symmetry that our theories seem to be begging us to make, whether we can show that that describes the world. So I've shown you quite a few ideas. I haven't been able to do justice to the logic or the beauty of all of them by any means, but I can heartily recommend to you a source for learning more. For all this in depth and much more, there's a wonderful description in this book, which you can now get. And I must say, the cover alone is worth the price. You open, and I can say this without being immodest, because I had nothing to do with designing the cover. So it's a peephole, and if you open up, you find this. It's a wonderful metaphor, I think, for the fact that we get glimpses of an inner reality from just looking at things, but then by acting on it and looking deeper, we find wonders in splendid exuberance, even more. Thank you for your attention.